Hi, welcome to EC3120. This is your TA Asif. Today we are going to talk about Lab 3, which is active current sources. So, what is the ideal behavior of an active current source? Any current source. So, the ideal behavior is it should be able to provide any amount of power. It will not depend on the load. It should be able to provide the same amount of current irrespective of the load. If it is a smaller load or a bigger load, it will be just providing the same 5 milliampere all the time or the 10 milliampere all the time. So that's what the ideal behavior we expect from a current source. But the output resistance, to understand the output resistance of the current source, we can take a look at a graph. As you can see, if you plot the voltage here and the current in this axis, then you have a line something like this, and you have a slope. So if you take the inverse of that slope, you will get the output resistance. And here we are going to build the current source with transistors. So the transistor should have a large emitter resistance. So if we think about the transistor, we should be having a very large resistance in the emitter region. But if we want that, we need a bigger area inside the IC, which is not desirable. And who wants a bigger IC? What we have here is like we have a wafer, then we have smaller ICs which we cut out of the wafer. But if our ICs are big, then we will get fewer ICs out of this wafer, which is not desired. So we don't want bigger IC, we don't want to waste our real estate inside that wafer, and usually the ICs use independent current sources. So our lab is going to be on active current source, but at the same time we should have some idea of which is a passive current source. The passive current source can be built with very simple arrangement like this. What we have here is we have a voltage source, here we have a very large resistance, and then we have the load. So what essentially happens is this load is so small compared to this resistance is you always get the same amount of current. Mathematically speaking, we can solve this circuit using the Ohm's law. So your current is total voltage divided by the total resistance. So if you have a very large RS, or this R large, then you can approximate this RS plus R load to be just the RS. So this doesn't play a part in the equation, so you always get V divided by RS. So this is kind of independent of R load, but as you can see, it's not very practical. You just have a extra big resistance sitting in between your source and your load, and you'll be wasting a lot of energy here. So this is kind of not desirable. So this is what a simple current source, which is active current source, looks like. So here let me show you something. If you just divide the circuit in middle, you can see there are a lot of symmetry in between here. In between the left side and the right side, you have a source, you have a resistance here, and you have transistor here, transistor there. So before we move to the next slide, let's note something here. This is the output current that flows around here. This is I1, and before we talk about the transistors, let's see the I2 is the current that flows here, and it's divided in two branches, the IB1 and IB2. We'll talk about the relation between I2, IB1 and IB2 in the next slide. Here we have to make some assumptions. The transistor Q1 and Q2, let's see where they are. Actually, there are only two transistors. This is Q1 and this is Q2. They are supposed to be identical. They are fabricated on the same substrate. They are on the same chip. They have the same technology. Then they underwent the same processing steps. So if this was processed 500 times, this is also processed 500 times, this is processed 10 times, this will be processed 10 times. So there is no different. I mean, they are from the same chip essentially. And keeping that in mind, we can fairly assume that they have the same gain beta, which is hybrid in terms of hybrid parameter HFE. So therefore we can say the gain of this transistor 1, beta 1 and beta 2, they're the same. So the beta 1 here and the beta 2 here, they are the same. And after that, if we think the junctions are identical, then the identical junctions will make sure that the current flowing this way and the current flowing this way, the IB1 and IB2, they are the same. So if we think the IB1 and IB2 are the same and I2 is just the sum of, actually there should be a comma, I just okay, there's a break actually. So the I2 is IB1 plus IB2, and in simply speaking, I2 is twice of IB1. Now these calculations might look a little bit terrible, but they're really simple. They're just simple KCL. Now I1, here's the I1. I1 is the sum of IC1 and I2. What does it mean? So here you have the I1 coming this way, and then you have the I2 and IC1 here and here. So we know what it is. IE1 is the sum of IC1 and IB1. That is kind of the simple transistors equation. Your emitter current is the sum of your collector current and the base current. So there's nothing new. And the collector current can be always written as beta times of IB1. So I just replace this IC1 with beta times IB1. And your base current is IE1 over 1 plus beta. So these are very simple transistor equations, so we know what they are. Now, what is this collector current? The collector current is IE1 minus the base current. So the collector current is emitter current minus the base current, but a few moments ago we saw the base current is this equation, so we just replaced excuse me, we just replaced this base current with IE1 over 1 plus beta. So here we have IE1 and IE1. We can write something like this, and finally we can write the IC1 to be beta IE1 1 plus beta, I mean from here, and that is our I output. What does that mean? Let's get back to the diagram. That means our IC1, which is here, okay, let me clear this thing. The current that flows here is the same as I output. So this I output is actually just a copy of this current. Now we'll see if that is the if this I output is the copy of this part, then how is it different from the I1? We can say this I1 has some relationship with that I output, but almost same. It's not exactly the same. We can say it's almost the same, and we'll also see it in terms of mathematics. So I1 here is the sum of IC1 and I2. So where is that IC1 and I2? Here is the IC1 and I2. They're just we're just using KCL at this point, and IC1 is this from the previous slide, and I2 is twice of beta, twice of IB1 or IB2, whatever you can say. So I2 was twice of IB2 or IB1, whatever you say, and the IB2 is this. So this becomes this and this becomes this. So we see the IE1 is IE2 is common in both the terms, so we can write something like this. Now what's the relation between the I1 and I output? just as I said, I output is IC2 and IC1, which is this. We use this expression here also. So we can just divide that I output with I1. So we are essentially dividing this term with, let me change the color to something else, with this term. So at the end we have something like this, and this gives us this expression. Now we can see that beta divided by 2 over beta is almost approximately 1. Why? Because it's if we remember, the beta is the transistor gain, and if you have a transistor gain of say 120, then you are actually dividing 120 by 122, which is approximately 1. So we are saying that I output divided by I1 is approximately 1. Let's get back to the bigger picture. So that's what I said. The current here is exactly same as here. The current here is approximately same as here. As you can see, we actually just missed the twice of that base current. One base current and the second base current, they're equal. So that's what this expression is trying to say. They are almost equal, just a little bit smaller. I output is almost a little smaller than the I1, but we can assume they're the same. And the value of the output current does not depend on the load on the Q2, and your R output is 1 over HOE if you think with the hybrid parameters. And the part 1 of our lab, well, this is all the tasks we have to do. We have to design an active current source. We have to look up for the specifications in the lab manual. Let's see what are the specifications are given. And load current is independent of the load resistance, and then you design, you simulate, and you build it. Now this is the required specification. That means you should have a slope like this. A slope like this means we will have 2 volt and this much current. If we are at 8 volt, we should have this much current. So what if you build a better current source? How can you tell? If you build a better current source, then your slope should be something like this, because the ideal one should be flat. So this is our expectation, and if you can build this, this is even better. And if you build something like this is actually not meeting the expectation. This is ours. So what about the output resistance? As you can see, we can easily calculate the output resistance. At 8 volt and 2 volts, you have this current and this current. So here this is 2.2 milliampere, and this is 2.8 milliampere, and this is the voltages. So the voltage difference with the current difference, you figure out the slope, and this is the output resistance. So something to think about in about the part 1. It does not provide a very large output resistance. It's just a 10K. Okay, so excuse me. It's not very big. And we used a small signal model to predict the large signal behavior. Like we just divided the, we just dissolved the circuit into small signal model, but we also thought about the large signal behavior. So this is not accurate, but this is the best we have, and we are not designing the best current source. We are just aiming to meet the set expectations. So our current source, something goes like this, it is not the best one, but this is the specification. So if we meet and if we get something like this, then we are happy and we have met our goals. So this is a little bit about the design. So this is an example. You can use this value, this current, and this VCC, this RC, and this RL, and you might be getting values somewhere that is expected out of this experiment. Now we have a second part which is called the Whittler current source, named after inventor Whittler. So it is a current source with higher output impedance than the simple current source. Like last time we had like 10K. Now we want something bigger than that. And better control of output current over voltage range. What does that mean? Like last time we were kind of like limited by this. So once a transistor is made, we don't have much control over this thing, but now we want a tunability, like we can do something, and it can replace larger resistors in ICs. So let's see what the expectations are. Output current should be 100 microampere, so it's much smaller current. Output resistance is to 200K, I mean bigger than 200 kilo ohms. Last time we did like 10K, so this is much bigger. The output voltage should be between 3 and 7. So as we can see, it is a little bit smaller in terms of range. Like last time we did 2 and 8, but this time we're just trying to think about like 3 and 7. The current should stay between 80 to 120 microampere. Typically I have seen the circuits usually attain like somewhere in between 90 and 110 microampere, so it's easily achievable. So just like last time, we can use KVL to solve for the resistors. So this is how it looks like. And what is the difference between this one and the previous arrangement? So if we think left side, right side, they almost look the same, but there is a difference here. You have that extra RE. You have an extra resistance which is attached to your emitter. And in this case, the voltage at this point and the voltage at this point are not the same. I mean, if you think about the very first circuit, we can use this circuit here, no problem. The voltage here is 0 and the potential at this point is 0 because they're essentially connected to the ground. But as you can see here, this one is connected to the ground and this is 0 and this is not equal to 0. It has some voltage over there. So the VBE2 minus VB1 is IE2 RE. That means the current that flows through this RE, which is IE2, going this way. You can just figure out the voltage here. So that's the difference between here and here. Technically speaking, VBE1 is actually 0. And this is the equivalent small signal circuit, and this is the values that we actually get. I output RE is this. So I actually skipped the part where we actually talk about the derivation, which is pretty tedious. It's in the lab manual. If you want, you can take a look at that. And the R output is given by this equation, and it is a really big expression. I should say it is a big expression, but we don't actually care how it came here. I mean, for this experiment you can just use this equation. If you are interested, you can take a look at the lab manual. The detailed derivation is out there. You can see how this equals this, but for this lab we just use this equation. Now these are the things that are due next week. You should complete the simulation before the lab meeting, design what resistors you are using, and you should write those down in your notebook, and then we should be good to go. And thank you, and see you on next week.